the another important difference is that normally these convolution layers are succeeded by, or after every convolution layer there is a pooling layer, which basically does kind of a subsampling operation. And the reason is that basically we know images, problem with neural network dealing with images are too, the dimensions of images can get too high. Even a 2256 cross 2256 images will have hundreds and thousands of pixels, and more pixels means more connections and more weights and more parameters that needs to be trained. So we would like to reduce these the size of the dimensions of the images in an effective way. So one effective way is kind of a subsampling operation, because once we extract features, once we do a convolution operation and extract features, we get these kinds of, these are just illustration, let us say these are like edge detectors and something like that. So we can see most of the pixels are basically black pixels, there is no response, and only edges and other locations only get a higher response. And we are actually only interested in those locations which have a higher response, and we are not these black or zero response pixels have no value for us. So after we have done a convolution operations, there is no information in these black or low value pixels, so we can try to get rid of them in an effective way. So one idea is basically just downsample it, just subsample it, and that is what basically is done in pooling layer. So we shrunk the output or the image by a factor. So we take a stride. We'll show how this pooling layer works. But basically the idea is we reduce the number of parameters by reducing the size. And also it is found that it also helps in some kind of a translation invariance at each level, because we are taking a local neighborhood, maybe let us say 2 by 2 or 3 by 3 or 4 by 4, and reducing it to one value here. So if your object or content is little bit shifted here in that small local neighborhood, it basically doesn't matter. So that kind of small invariance also it helps. So that normally it is done a 2 cross 2 or 3 cross 3. We take a pooling operation is done on 2 cross 2 or 3 cross 3 window, and the operation that is done can be either an average of all these pixels or mean value or just max and min. Most common is the max operation, because of the same reason that we said we are interested in picking the pixels or the response which are higher, and we are not interested in low response. So we can just take a max of in that local neighborhood, and in that way basically get rid of those non-responsive regions. So let us just see one example. So this is an example of a max pooling layer with a 2 cross 2 window and a stride of 2. So we will take this 2 cross 2 window, and basically, so in the first layer, this first location, you take the max operation, so you take 6. In the second, basically you get 7, and so on. If you continue this, you basically, and we are moving a stride of 2. If you see, we are taking stride of 2, so we are skipping 2 rows, then going to the next location. Similarly, when we move forward and come down, we also skip 2 columns also, or 2 rows also, and we come down straight away to the next location, and so on. So this way we subsample it by a factor of 2 in each dimension, x and y, and we get this output. So we have retained a max response and got rid of non-responsive locations. And the last thing that is a difference in our CNN is, normally as an activation function we use a ReLU in CNN is the most common choice. And the reason we have already talked earlier, because in a neural network most often there is a tan or a tan-h or a sigmoid function or logistic function. But those things, there is two things that there is a problem there. When the gradient is at these locations, the gradient becomes very low. So it basically leads to it slows down your training, because your gradient flow your gradient starts vanishing gradient problem, I think you must be aware of. Whereas in ReLU, basically because it's a linear curve, so the gradient remains same at all locations, and so it trains much faster. So it accelerates the convergence of your stochastic gradient descent algorithm due to linear non-saturating form of ReLU. And another important advantage with this ReLU is it's a very less it's less expensive operation. So computation of tan H function or sigmoid function involves exponential and all that, whereas this is simple thresholding. So if it is greater than 0, if you take just x, if it is less than 0, you make it 0. So it's a simple thresholding operation, and which is more easier to do than comparison to tan and sigmoid. So ReLU turns out that ReLU actually helps training or convergence of your training much faster in CNN. So the first successful convolution net was long back. In fact, it came out in 1998 or 2000 somewhere. It was called LeNet because by the name, the main scientist Lee Kun at New York University, they had basically proposed this architecture for this MNIST data set basically, and their architecture performed around 99, more than 99 basically % accurate. And we can see it had almost most of the features of the modern convolutional net. There were so the input here was not, it was just a grayscale, so there is no depth here. So initial input, it preserves, it takes the input as it is 32 by 32, applies 6 convolution filters, and so you get a 28 cross 28 feature maps. And then there is a subsampling, which is basically a pooling operation, followed by another 6 filters, convolution filters of some size. The size you can calculate, but these are some size, and at the end basically it is having full connections. So ending up for a classifier purpose. But instead of softmax, they had some Gaussian connections and all that. But most of the features are very similar to the modern architectures. And also instead of ReLU, they used logistic activations, so which is basically your sigmoid kind of thing. And it performed well for this kind of an MNIST data structure or data set. And the number of errors made by this, of course, they improved. So there are different versions of this. So the first version was in 1998, and after some years they improved, and probably the best version of that version was called LeNet 5, and it only made 82 errors out of those 1000 training samples. So I think it had 10,000 training test data set, so 50,000 training and 10,000 tests. So out of those 10,000, only 82 errors were made, and out of these you can see some errors even human would make. So for example, this if even human will read as 1, but the actual label of this is 2. So I think the human error rate will be around 20 to 30 errors out of this. So it comes quite close to the human error rate. Even this, for example, this looks like 9. This looks like 4 also. You can see it can be interpreted as 4 also by human also. So there were several such cases you can see. So there was some improvement done by other people also over this. So there was this person who basically did nothing but simply augmented the data set. So he basically used this augmentation technique, which is also a very popular technique which is used nowadays. So if you have a data set and data set has less samples, or MNIST has only 10,000 samples basically, or 50,000 samples, for each category maybe a few thousand samples. So by augmenting the data set, generally the training performs better, because if you have less samples, generally that the model tends to get overfit. So, but by increasing the number of samples, that overfitting could be avoided. So data augmentation was done by this person, and data augmentation is very simple in images, because he basically did many different transformations. So slight rotation, slight scale, slight different rotations, and simple contrast enhancement, either some slight variations, simple affine transformations, so that the object appearance did not change too much. But you also got capture different variations of that particular digit. And in that way, basically, they achieved up to 35 errors. So from 82 errors, they could reduce to only 35 errors, which is quite close to the human error. And you can see, in fact, that if the top two guesses of that error were always the correct, even for these errors, which so this is the actual label, and they predicted 1. The top error, the top prediction was 1, and the second prediction was 7. And even we could probably read it as 1 and 7. But others, for you can see the right prediction is almost either in the second prediction, in the first prediction or the second prediction, the right. So if you take the top two guesses, the error rate would be almost negligible. So and you can do some kind of a model averaging. One, you can take you can take an averaging out of the two and to improve on it. But these were small, and these did not really brought any attention to this. The thing which actually changed the whole scenario was two things which actually brought the discovery. One was development of a huge data set. So till before ImageNet, we had only maybe few thousands or maybe 10,000s of samples of images in a data set. But the first large data set which came out was ImageNet, which was a humongous size data set, 14 million images, and it had around 22,000 categories. And those categories were taken from basically WordNet. So WordNet is a basically English dictionary kind of a thing, and with connections between words and their synonyms and all those things. So some the same labels were taken as the categories in this, almost similar labels and the connections. And they actually did a huge job of collecting 14 million images from internet and labeling them using Amazon Mechanical Turk. So paying them using online workers and paying them a few bucks for labeling the images with the things. And this data set was a very huge challenging data set for this task. And every year a challenge will be a competition will be held on this, and most often a subset of this challenge is taken, because this image, the entire data set has some ambiguity also amongst these 22,000 categories. Many of the categories are just for dog class itself, maybe different breeds or breeds of dogs and so on. And some of them, maybe there's an overlap between categories. So within a particular animal, there is one category of, let us say, dog, and within them there are different hybrids, different categories of dog. So if you take out those distinct categories and so that subset is taken, which is mostly used for testing a model that has only 1.2 million images and it has only 1,000 categories. So on this data set, this every year challenge was basically done, and people would basically come. The winner would be basically found out, and most of the winners before this, the first net, which actually, so most of the, as earlier said, most of the earlier methods which were using SVM and some handcrafted features, their accuracy would be bordering around for 50 to 60% maximum. But this AlexNet, which was the first CNN-based architecture that came out in 2012 competition, so it basically decreased the error rate from 26%. So this is the top 5 test error rate, not the top 1 test error rate, from 26% to 16.14%. So which was a huge jump. Earlier, maybe a maximum every year, maybe a difference of 1% or 0.5% of this would be coming out. But this was straight away order of magnitude of jump. And this architecture is the traditional now, which is now a very popular convolutional neural network architecture. As you can see, so he resized the images to a size 227 cross 227, and this was a color image. So first layer had kernels of size 11 cross 11, and I think 96 such kernels they used, and then followed by max pooling layer and so on. You can see, and the last two layers are fully connected layers to stretch out, and then the final layer is, because there was 1,000 categories, so you end up into 1,000 neuron classifier. So Why it took so long? 2000, why only 2012? Why not before? Because GPUs, which were mainly used for earlier for only for rendering purposes, they were not available, and they started coming for general purpose computing. GPU cards and GPU architecture started coming around 2008 and 2007 for general purpose computing, and it took some years before some basic libraries could be developed for GPU based computation. Basic BLAST library, which is basic linear algebra library, that come out in 2009 or 10, and then using them, this person basically was working on his PhD on using them, and by 2012 he implemented the components of a CNN on GPU. So all the convolution operations and this pooling operations, all those things, he basically implemented it on GPU architecture. So GPU requires a different programming than a normal CPU kind of thing. So that requires some effort, and that took some years. And his software, which is called CUDA ConNet, was basically the first library, you can say, for CNN or neural network based computation, and that allowed around a speed up of 100 times speed up as compared to a normal training on a normal CPU. So earlier on CPU, it would take many months to train even a simple this kind of function neural network with just 3-4 layers. It would take many months, but with GPUs, it reduced to few weeks on ImageNet, and which made it possible basically to do that. And this idea of using CNN plus GPUs actually brought this revolution. So these were two things: advancement in the architecture, in the modern computing hardware availability of that, and also availability of larger data sets, challenging data sets, and coming up with this CNN architecture. So these combination actually gave a breakthrough. And this I will like to skip. So what these AlexNet layers are learning. So first layer is very easy to visualize, because first layer you can see the filters are just 11 cross 11 cross 3. So you can visualize them as a simple color image. And you can see these, the first layers are learning gradients, or maybe gradients in color, or blobs, or patterns, or some kind of textures also. So these are what is getting learned in the first layer. And but the subsequent layers are very difficult to visualize, because you can see the dimensions becomes very huge. It is a 96 dimension filter size, and if you visualize each dimension as separately, you just get this kind of patterns, but you cannot infer from them. And visualizing a higher dimension filter is hard. So they used some techniques some work was done on visualizing these CNN, what features these are CNN layers are learning, and they use some data flow methods by which they could learn that different layers were learning some. I am skipping this, but they could verify that some meaningful part of the image which was basically the focus of that particular class. Those things were getting learned at different layers, and they could do it for each layer. So instead of basically optimizing once the network was trained, so instead of optimizing the weights, they could, like, now if they want to see which neuron is getting fired by which features, they would reverse the task basically, and they would modify the image using this propagation and other kinds of things to know which particular neuron is getting fired or getting activated by which kind of images in the input. And they basically try to generate those images which basically responds to different layers, to neurons at different layers. So early layers neurons were getting activated by these kinds of images which have these kinds of patterns like blobs and textures and other kinds of things. And progressively higher layers would have patterns like curves, edges, eyes kinds of things you can see, and later layers would be having even faces of. So probably this data set had many samples for dog classes probably. So the dog and cat classes, so they would learn by doing these kinds of generating those artificial images. Many of those later layers images would be having those faces of dogs and cats and so on. So that means it was intuitively these things was working basically. It was what we wanted basically, that we should first extract low level features and then the subsequent layers should extract more high level features. That was indeed being learned by this training of these CNNs, and that partially explains the success, the high accuracy that you get. And there is a real online CNN model that runs on Stanford University research group, and you can see it basically changes in real time. It changes these images from the ImageNet and shows the prediction from that CNN things, and you can see it does quite a good job of predicting the accurate. The first prediction is most probably the actual ground truth label on some images. For example, this images which is a, because there are two objects here, so this has been classified as a cherry object, but you can see this dog is also a major portion in this. So because there are multiple objects present in these images, so probably this CNN was predicting the species of that dog as the output rather than these cherries. And sometimes the object may be occluded or deformed, and so the prediction would not come out as that. But so that is, it's a challenging data set. So you can see, so after these traditional layers, the AlexNet layer had a jump of around 10 times, or but not 10 times, but a factor of 10 or 20. And similarly, the next every year then a new model would be coming out based on CNN only, some modifications. So then by Oxford Group, VGG, Visual Group Computing and things, and then from Google next year new architecture came out, then from Microsoft, ResNet and other things, and they have steadily improved the accuracy and started saturating. So the top 5 accuracy has been now, of course these are older slides, probably now we have even very close to the human error rate. So I'm not going to talk or dial. So in my slides now there are details of VGG and GoogleNet and ResNet and InceptionNet architecture. I'm skipping these discussions because we don't have that much time. There is a in my Teams video, these models have been discussed in detail. So if somebody is interested, he can actually watch that video. But now basically after so after the successful application of CNNs on image classification tasks, the research community started applying these on other tasks, other computer vision tasks like segmentation, object detection, captioning the images and even videos, and activity recognitions and so on. So those tasks are there, and of course we will not be able to cover all of them. These two we will cover in the next week, segmentation and object detection. So but before we conclude this topic, there is another important thing in CNN that is done, which is called transfer learning. It is not unique to CNN. It is a general technique in ML, machine learning, but it is most often used in deep learning, because what this transfer learning process is basically, so you take a model which is trained on one problem, on a source task, on a particular domain like ImageNet, and then you reuse that model as a starting point for another problem, for training a model for a second related problem. So you adopt that. So instead of, so problem is in deep learning, if you have to train a model from scratch, you need a data set which has sufficient amount of samples. You need a large data set. You need GPUs and good amount of computing hardware, and still you have to also need training time. You have to be patient enough to train it for probably few weeks and see and tune on the parameters. So it takes time to tuning a good, coming up with a good model, training a good model on a new task from scratch. So instead of doing that, because what we have seen is that suppose we have a model trained on ImageNet. So the earlier layers, most of the convolutional layers are generally learning general features like edges, or which are general features which can be used for any other domain or any other type of task, even object detection or segmentation. And so, or it can be used for another data set. So you may be you may be like try so different variations are possible. You can use the same domain, so you can basically use the same data set, but you can do a different task. From instead of classification, you can do now object detection or segmentation, or you can go to a different domain. Maybe instead of ImageNet class, you may have, let us say, data set of your classrooms. Like we are collecting data samples. We are making a data set of classroom images, and so it is an example of a different domain. But if you have to train our model, deep learning model, on all those things, we need all these things. We need a good hardware. We need a large data set, which is very difficult to collect and label. So what we do, basically, we do transfer learning. So whatever these, so most of these famous models, VGGNet, InceptionNet, ResNet, and all these things are, these companies, they release these models. And so in fact, NVIDIA does this task regularly. So they regularly keep on releasing the most optimized and best performing models for different libraries and all that. So you can use those pre-trained models, which have been trained on general data set like ImageNet, and then basically that so you may be now targeting a different data set, and you may have different labels or different number of classes. Instead of 1,000 classes, you may have only 10 classes. You may want to just train 10 classes on that, and so on. So your target task may be different, your target data set may be different, but you use essential part of that model. So how do you use that efficient part? This I'll skip. So this is an example of, if you maybe instead of training on ImageNet, you can train on Pascal dataset. Pascal dataset is much smaller dataset with a different purpose. So it is hard to train a deep neural network on Pascal dataset because you just have probably 5K training images. So generally model overfits. So, but you can do this transfer learning. So what you take the pre-trained model, and you basically preserve the initial convolutional layer weights of those models. So you freeze them, and you change the, so what because we know that the earlier layers are more general, and the later layers are more specific to the particular task that has been trained, or the particular data set that has been trained. So you start modifying your model from the last layer. So initially you just modify the classifier itself. So you, instead of softmax, if you want some other classifier including SVM or whatever, you can do that. Or instead of 1,000 classes, you may want only 10 classes or prediction or something. So do we again train on different data set, or simply use the model for our data set? Yeah, so now we'll be using our data. So if our data set is different, so that depends whether you are using a different data set or not. If you are using a different data set, you can use a different data set also. And but how you start changing this model, tuning this model, you start from the last layer. So you first change the classifier itself, because now most oftenly you will be predicting different classes, or you will have different, your task will be to detect different objects or different classes. So you have to first change the classifier. So you freeze the weights of the initial layers, and you only change when you're training on your new data set, you only change the classifier. So you start from the last layer, you train only parameters of the last layer and see how it is performing. If not, you go further back, you change you unfreeze the either change the layer architecture, or unfreeze the weights. You relearn the weights on the new data set or for the new task, and slowly you keep on experimenting, training. And what often is found, that if you are doing a related task, if you're training on a related task on a related domain, most often you don't need to train the initial layers. Just changing the last layer parameters result in a very good accuracy very soon. So you basically reduce your time of training, and you get a huge progress in your training of your model by this kind of a technique. So that is what is done mostly nowadays, because most of the companies or people working, they don't have that much resources to train from scratch. So they take mostly the pre-trained models and start from there, basically. That is one approach, of course, but all the time it may not work, because your data set itself may be very small, and that even using these pre-trained models may not do a job. So in that case, you can start from scratch also. You don't need things. You don't need a pre-trained model for that. But in general, these techniques do work well for deep learning based methods, especially for CNN based methods, because the initial layers are more often learning only very generic features which work in different domain and for different tasks. So that's with that we end the topic of CNN, and these are some references based on which this entire content was taken for CNN. We took the content from Stanford University course and from this university, and then we use this online book on neural networks and deep learning by Michael Nielsen, which is very easy to understand. So if anybody is interested in understanding more details, so we have done a little bit fast coverage. More details if you want to understand, I would recommend these 3 resources. These are very easy resources and nice resources to understand this topic.